I want to talk about a physics concept called work. Now, there's a bit of a problem because work in English has a certain meaning. If you say, I'm doing work, I'm putting work in, you mean I'm getting tired. Work is not tiredness. There is a physics concept that will also explain tiredness, and we'll talk about that during this unit. But in physics, work, Nick, has a very, very specific meaning. It does not mean doing something that makes you tired. Instead, wow, that was a little strange. Instead, you do work on an object. You don't do work, you do work on something. And Lena, if you're going to do work on an object, two things must happen. Number one, an unbalanced force must act on the object. And number two, the object must move through a distance in the same direction as the force. In other words, here's the punchline. Work is calculated by force times distance. I'm not going to put a times sign because if I put the letters side by side, that means multiply. So work is FD. But the force and the distance have to be in the same direction. Is work a scalar or a vector? It's a scalar. That's going to be really, really nice. That's why it's going to be so handy to analyze things like roller coasters, where they're constantly changing direction as they go up and down a hill. Okay. What would the units for work be? By the way, let's draw a little box around scalar just to remind ourselves of that because it's important. What would the units for work be? Well, what are the units for force? What are the units for distance? So the units are Newton meters. But this concept is so important, we give that a special name. We call it a joule, symbol capital J, named after a scientist whose last name was Joule. Work is measured in joules, but a joule just happens to be a Newton meter. So for work to occur, force and distance have to be in the same what? Looking for a word that starts letter D. Remember that, remember that, remember that. And there's a second condition. The force has to be constant. If you have a changing force, this equation doesn't work. Where might you have a changing force? We'll really run into this in Physics 12 when we look at space mechanics and orbital mechanics and gravity. Because as you go further and further from Earth, what happens to the force of gravity? And that means you can't figure out how much work it takes to put something in orbit. Why would I care? Because you're going to learn in this unit that's actually how much rocket fuel it takes to put something in orbit. But unfortunately, rocket science is going to get a little more complicated because it's not a constant force. It's rocket science. Example 1, I like example 1, I like example 1, I like example 1. Example 1 is a nice question. Danica, what's example 1 asking me to find? How much work, you say? Keep reading. Stop. A trigger word is going to be the word lift. I'm going to do a fairly lengthy argument in a few seconds, and then I'm going to say, can we just agree that I don't need to make that proof again? Anyways, from the ground to a height of? Okay, what does this want me to find? Well, first thing I would write is work equals force times distance. In fact, it's going to be the force that you lift with times distance. F lift. Write an equal sign. Leave a space, and instead of distance, I'm going to call it H for height because it's vertical. But we're going to put something in front of there. What am I lifting with? Well, you know, let's draw a free body diagram over here. What are the forces? Let's suppose you're lifting something. What are the forces acting on this object? Get the obvious one. What else? I kind of gave you a hint in the equation there. F what? Lift. Let's assume you're not trying to speed up or slow down. You're just doing the minimum amount of work. So let's assume that F lift is the same magnitude as gravity. Okay? So now that I've done that argument, let's read the question again. Danica, what do they want me to find? Done what? What's the word I underlined? So it's going to be F lift times D. I don't know F lift. Oh, but look. I know another force the same size as F lift. What? More specific, can you read me the two letters? What? And let's write work done by lifting equals mgh. Don't add that to your green sheet. You'll end up memorizing it without meaning to, trust me. But the work done by lifting is going to be M 12 G low negative. Oh, we're no scalar. We're in Scalarville, so 9.8. 9.5. What do you get? I get 1,152.4. I'm going to call it 1,150. Danica, units. Joules. Direction, none. Not like momentum. Work is a scalar. Is that a lot? Well, 12 kilograms bowling ball. Is that right? Am I wrong? Oh, you know what? I went 12 times 9.8 times 9.8 instead of 12 times 9.8 times 9.5. How about 1,120? Is that better? Thank you for pointing that out. I do make mistakes. Is that a lot of work? 12 kilograms, Nick, but a bowling ball. 9.5 meters, about, I don't know, 3 stories. So carrying a bowling ball up 3 flights of stairs, you know what? Every one of you could do that. Would you be tired at the end? It depends how fast you did it. Tiredness, we'll talk about this next lesson, is actually how fast you do work. It's not how much work you do. It's the difference between walking up a flight of stairs and running up a flight of stairs. Walking up a flight of stairs, meh. Running up a flight of stairs, okay. Example 2. Can you cross out the word coal? Can you replace it with the word Zach with an H? Zach pushes against a brick wall as hard as he can for 12 seconds. Amazingly, the wall does not move. Zach, could you stand up for me, please? Behind you is a brick wall. It's painted over, but there's brick underneath there. So can you find an empty spot on the wall? Can you push against it as hard as you can? Push against it as hard as you can. Put your back, keep pushing for 12 seconds. Push. 1, 2, 3, 4, 5. Push harder. 6, 7, 8. Keep pushing. 9, 10, 11, 12. How much work did Zach do? Well, Lena, what's our equation? Work equals what times what? It's in the box. W equals what? Did I do a box? I think I did a box. No, I didn't do a box. It's here. Now it's in a box. Did Zach apply a force? Did the wall move a distance? How much work was done exactly as a number? Even though he might get tired if I made you do that for an hour, this is why I'm saying work is not the same as tiredness. Example 3. Pushing a box along the floor requires a steady force of 22.5 newtons. If you push it for 13.6 meters, how much work have you done? Nick, what's this asking me to find? How much what? Yep. How do I calculate work? And by the way, you should probably see where this is on your green sheet. So I did give it to you on your green sheet, and we're in that area now. Force times distance. Is there a force in this question, Nick? Yeah. Is there a distance in this question, Nick? And everybody, based on reading this, are the force and the distance in the same direction? They seem to be, so we will have work done. It's going to be 22.5 times 13.6, which is what? Sorry? 306? Units. Joules. Direction. Much like your future, there is none. Right? Example 4. Dylan pedals his bike up a 19-meter high hill that's 91.4 meters long. The combined mass of the rider and bike is 65 kilograms. The bike requires a steady force to continue up the hill. He's not going to speed up or slow down. Suppose Dylan used a rope to climb vertically up the back side of the hill. Suppose he hooked the bike onto his back and he climbed vertically that way. How much work would this require? It's a good question. Ashley, how do I calculate work? And I guess this would be the force done in lifting his body. Oh, when you lift something up, what force is that exactly the same size as? This is going to be mgh, to climb the back of the hill. M, was it 65? G, 9.8. H, 19. If we wanted to climb the back of the hill, or maybe there was a stairwell that allowed me to just put the bike on my shoulder and climb straight up, how much work? Do you get 12,103? I'd like you to write all the sig figs for a reason this time. 12,103 units, Ashley? Joules. How much work will Dylan do riding his bike up the hill? It's a good question. How much work did Dylan do? Oh, that's a bad color. You can't see it from the back. Let's get darker. How much work did Dylan do lifting it straight up? 12,000. What was it? What if the ladder had been tilted just a tiny bit? Or what if it had been tilted a bit less? Or what if it was on an even shallower angle? Like the bike hill. Here's the beauty. When you're going up a hill, what force are you doing work against? What direction is gravity? Vertical, up, down, but in the vertical direction. If you know your vertical height, that's the work. Same answer. The work you do climbing up the staircase that spirals is the same as the work that you would do if there was a fire pole or a rope in the middle and you just hauled yourself up hand over hand. How's that? Patience. What if this hill was really shallow? I wouldn't have to pedal as hard because it's not as steep. I would be exerting a smaller force But you know what? I'd be traveling a bigger distance. Same work. What if the hill was a bit steeper? Shorter distance, but you know what else? Bigger force to pedal up a steeper hill. Same work. What if the hill was even steeper? Shorter distance. In fact, you know what? The shortest distance is straight line, but that would be the maximum force, mg. All hills do, all ramps do, all stairs do, is they increase the distance so that we don't have to exert as big a force. We end up doing the same amount of work. We spread it out over more time. It takes longer to go upstairs than go straight up. Same amount of work. So both of these, because you're raising yourself 19 meters against the force of gravity, you're going to do 12,103 joules of work. Brea, what's C want me to find? Using your answer from A, calculate the force that, well, my answer from A was work equals force times distance, but now they want me to find the force that Dylan pedals with. Okay. Get the force by itself. How will I move the D over? So, yet another equation for force that I'm not going to memorize. Are you telling me that force is going to be the work divided by the distance? How much was the work? 12,103. Now let's go look back at this picture. I think the force pedaling would be in that direction. I think F pedal would be in that direction. What did we say about the force and the distance when you're using work? The force and the distance have to be in the same, starts letter D. Which distance am I going to use here, Brea? Hint, not 19, but what? Instead of having to exert, by the way, if I just go 65 times 9.8, if I go straight up, I have to be able to exert 637 newtons of force. The hill, which was shallower, allowed me to only exert 132.4 newtons of force. But the trade-off was, got to do more distance to get the same amount of work. Okay. We say that a ramp is a simple machine. In physics, what's a machine? It's something that reduces the force but increases the distance. You're still stuck doing the same amount of work, Zach, but you don't have to push as hard. You just got to push it further. Turn the page. This is one of the nice characteristics about work. It's a scalar. It doesn't care what path you took. So what if the hill, instead of being a nice ramp with a nice straight line, how much work would it take for Dylan to ride to the top of this hill? 103 joules, because it would still just be mgh. All work cares about is where you started with and where you ended with. It doesn't care about what you did in between. And on a basic level here, Lena, we raised our height by how many meters? 19 meters, mgh. Hey, what takes more work? Lifting a 25 kilogram mass to a height of 4 meters or lifting a 50 kilogram sack to a height of 2 meters? Okay. So work equals force times distance if the force and the distance are in the same direction. What if the force is not constant? What if it's changing? You're going to end up with 3 different ways to find work. The easiest one is force times distance. It's also the most useless. It only works in certain conditions. Another definition for work, Keegan, is it's also the area under a force versus distance or displacement graph. Raj, what's example 7 asking me to find? Keep reading. From 2 to 5. Okay. What does it want me to find? Don't write this down, but look up. Why can't I go like this? Because how big is the force at the beginning versus how big is the force at the end? The force is changing. So I can't go force times distance. But what else did I say? Work is also what, Raj? A what? Force versus. Okay. Where are we moving from? What to what? Everybody do a little dotted line right at 2 meters. Do a little dotted line right at 5 meters, like that. And then after you've written the dotted lines, don't write this next little bit down. This is the work, that area. Don't color it in yet. What shape, don't write this down, do we call that? It has a name. Starts with the letter T. It's a trapezoid. Trapezoid has 2 parallel sides and 2 not. Anybody know the formula for the area of a trapezoid? There is one. And every once in a while I have a nerd who knows it. Anybody know? We don't teach it, and the reason is it's redundant. You don't need it because any trapezoid ever drawn under a graph can be broken into a triangle and a rectangle. And those you have seen area formulas for. So I said, don't write this down. What I would love you to do, please, is draw a little dotted line like that. And then if you want to, you can kind of do a little color, I'm going to call this area, area 1, and I'm going to call this area, area 2, A1 and A2. So, Raj, the work is not going to be force times distance. It's going to be area 1 times area 2. How will I know to use this method? They're going to give me a graph. In other words, if I scroll through the homework here really quickly, oh, I bet you I'll find the area underneath this graph for work. But I don't think I used it on any of these questions. Okay. Raj, what shape is area 1? Starts with the letter T. Triangle. Anybody know what the area of a triangle is? Yeah. Mass times width. Usually we write it as base. I write it as base times height over 2. Did I give you the area of a triangle in your green sheet somewhere? I can't remember. It might be on the data page on the back next to the chart that has the metric stuff. Did I give you some area equations there? Okay. So if you don't know the area of a triangle, I guess I'll let you add that to the front page. Maybe near where the energy section is, because that's where we're going to, near where the work equation is. So you can say this. Area of a triangle is base times height divided by 2. If you didn't know that. So, Raj, how long is the base of my triangle? Well, what number is right here? What number is right here? In your head? 3. 3. Okay? Now, no, I'm glad you did that. Raj made what we call in computing a fence post error. Instead of counting the gaps, he counted the hash marks. We call it a fence post error because if you're building a fence, if each of these is 1 meter 1 meter. How long is the fence? Everybody? How many fence posts did you need? 3 to make a 2-meter fence. You run into this in computing when you're writing code and you're doing a sorting algorithm or you're trying to do something. Especially, I remember spending 2 hours in a computer lab my freshman year because I'd written some software. It sorted a list perfectly, except the thing starting with an A ended up after the Z. That was its only mistake. And I had somebody came along, yeah, you did a fence post error. You were counting gaps when you meant to be counting posts, or you were counting posts when you meant to be counting gaps. So what's a better way than counting, Raj, to find the length? 5 minus, there you go. What's the height? How high here? How high here? Here. Ready? Look at the scale. What must each one of these be? Okay, so how high? How high? Ready? How high right here? You said it. Start. Sorry? Yes. Okay. How high right here? So, what's the height? Help them out, folks. 6. Base times height divided by 2. Oh, that was painful. You back? Going to redeem yourself because what shape is the second area? What's the area of a rectangle? Okay. What's the length? Okay. You know you're staring at the board. It's on your sheet too, right? You can look at your paper. 3. What's the height? That's this distance right here. There you go. Oh, let's keep going just for giggles. What's 3 times 6 divided by 2? You know what? Let's do 6 divided by 2 first. What's 6 divided by 2? Plus? How much work? Units? I like that question. I like that question. I like that question. Although actually that's too easy. I know he made it look challenging. I'm going to ask you on a test to do something with this answer, but you don't know enough about work to do something with it yet. So we have 2 definitions for work. Work equals force times distance. This requires a constant force. Work is also the area under a force versus distance graph. How will you know to use that one? The question will give you I'm looking for that starts with the letter G. Graph. Force versus distance. Next page. How much work was done in moving this mystery object 10 meters? Why can't I just go work equals 30 times 10? Why can't I go force times distance? What was the force at the beginning? What? What was her 30. Is that a constant force? Can't use that. So I guess, since they gave me a graph, it's going to be this area. Oh, wait. I would break it up into triangle and rectangle. Would you like a chance to redeem yourself, kiddo? Okay. Man, show them how it's done. Okay? So, work is going to be what? Area 1 plus area 2. Let's show your brother up. Area 1 is a triangle. How do we find the area of a triangle? It's base times height over 2. Area 2 is a rectangle, base times height, or I usually think about it as length times width. Right? Right. Okay, so let's plug in our numbers. How long is the base of this rectangle, my friend? 10. Not 2? 2 squares. 10. You gotta look at the numbers. Good. What's the height of this rectangle, my friend? That's the height of the rectangle? 20. Oh, we're doing the triangle. Sorry, we're doing the triangle. We're doing the triangle, not the rectangle. We're doing area 1. So ready? Sorry, that was my fault. What's the height of the triangle? Careful. 10. And then divided by 2. There's base times height divided by 2. Plus, what's the length of the rectangle? What's the width of the rectangle? Good. Hey, what's 10 times 10 divided by 2? What's 10 times 20? 20 times 10. What's 200 plus 50 in your head? Units, work. Look over at your brother and just shake your head in pity. Just come on, give him a little head shake. No, you had your chance. No excuses. Okay. You're either going to have, if I give you a graph, it's either going to be something like this, where the area is just a triangle, or it'll be something like this, where the area is a rectangle, or probably something like this, where the area is a trapezoid, which is a rectangle plus a triangle. It's going to be one of those three. Probably the third one, because why not? Example 9, a box is being pushed along a floor that has a mu of 0.25. The fact that they gave me a coefficient of friction, I'm already thinking this might be a job for a free body diagram. I don't know. I'm going to keep reading. The person pushing applies a force of 525 newtons over a distance of 22 meters. Okay. Ooh. Okay. Marcus, what's A asking me to find? Work is going to be, well, force times distance. How do I know? They didn't give me a graph. I noticed they used the word applies for the person, so I think that's going to be F applied times distance. Fair enough? A little leap there. How big is F applied? What's the distance? And I'm imagining this, are the force and the distance in the same direction? They are. What do you get? I'm going to write down everything for a reason. So 11,550 joules. Ooh, B. Huh. Emma, what's B want me to find? Work done in overcoming friction. You know what? I think the work done in overcoming friction is going to be the force of friction times distance. Fair enough? How big is the force of friction? I don't know. This is a job for a... Here's the box. What are the forces acting on it? Get the obvious one. Get the obvious one. Had me worried for a second there. What else? Go systematically, kiddo. What did we usually do after gravity? Yeah, is it sinking in the ground like quicksand? And I think normal force is the same side as mg. I don't see any upwards or downwards forces. What else? What else? And I think friction is smaller. The reason I think friction is smaller is it did tell me the box moved 22 meters. If friction was smaller, it was bigger, the box wouldn't have started moving in the first place. Fair enough? Okay. Well, let's go back to our equation. Emma, friction is what times what? Times distance. I don't know the normal force. Oh, but look. Another force the same size as a normal force. So I think in this case, I can say the work done by friction is going to be mu mg times d. It's going to be 0.25 times 124 times 9.8, there's mg, times 22. You all get 6,683.6? Yeah? Wait a minute. I got a bit of a problem with this. I said to you, when we defined work on the very first page, that the force and the distance had to be in the same, starts letter D. What direction is the distance in my free body diagram? I'm pretty sure to the right. What direction is friction? What would be a good way to show that the force was in the opposite direction of the distance? What's that negative telling us? We lost work energy to friction. We put in 11,550 joules of work energy, but not all of it went into making the box speed up. Some of it just went into heating up the floor, friction. How much? Over half. C says, what's the net work done on the box? So the net work, what was actually done on the box, the amount of work that went into making the box speed up is going to be 11,550, take away 6,683.6. This is what was left over to make the box speed up. 11,550 minus answer button, and I get 4,866.4 joules of work. So work is a scalar. Mr. Duick, if it's a scalar, how come you called that negative? This wasn't a direction, this is an energy loss. The amount, the magnitude went down. So you can have a negative scalar. Just means the answer got smaller. What's your homework? Well, work on the study guide if you haven't finished the momentum study guide. Prepare for your test, make sure you don't have any missing assignments. What's your homework for Thursday? If you don't want to have any homework over the Christmas break, I will be doing a lesson Thursday as well. Friday we'll have a little fun. But you can try, I think, number 1. Number 2. Number 3. You can skip number 4. Ha 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 ha. 5 is good. 6 is good. 7 is good. 8 is good. Are you going to assign everything, Mr. Duick? I don't know yet. Sure, 9 is good. Yeah, 10 is good. I'm going to assign them all. You're a mean one, Mr. Grinch, Mr. Duick. Sorry.